And then this is probably the presentation one, because the satellite system, which the sequence leaking test is based on, is composed of both two parts of the software, one inside Arduino, one on the computer, as well as a few pieces of hardware. So today we'll be focusing on the software part, and specifically the software installed into the hardware. And if we have extra time, and we can talk more about the satellite viewer, which is the computer part of the software. Okay, so first, to make sure everybody is on the same page, we'll have a brief introduction to the hardware. So this is Arduino, and this is a famous Arduino Uno, in which you see like almost everybody in Jeremiah Cohen's lab uses this. But the problem of this is it's mainly for it's useful mainly for learning purposes and for simple projects, because its computational power is not that strong. It's actually pretty low. A lot of people realize that, and that's why the third party, Teensy is one of many third parties, and they build their own what's called the developmental board, and it has a long history. And here a column shows all the models. So in the lab, we have Teensy 3.2 and Teensy 3.5 and 3.6. And 3.2 is the shorter. It's a shorter board, about this long, and then 3.5 and 3.6 are longer ones. So I have a 3.5 here, and not the entire thing, but just this little stick here. So there are many differences among these hardware. The most obviously is the number of channels. So you have more pins on the 3.5 than 3.6, obviously. But internally, 3.5 and 3.6 are faster, so which you can see from the rated speed here. And the difference between 3.5 and 3.6 is that 3.5 tolerates 5 volt, so you can safely interface with basically any kinds of digital peripheries that we commonly use. But 3.6, when you use that, you have to be careful, and it only handles 3.3 volt. If you hook up 5 volt to it, there's a risk of like damaging the CPU, or it's not likely to damage the CPU. Yeah, but as a cost, the 3.5 is slightly slower. So in terms of 3.2, it is 5 volt tolerant, so it's also safe to use that.
What does the rated speed mean? Like, what is it faster at if you go to 3.6 versus 3.5?
Oh, the rated speed here. So what is it, right? So the CPU has a speed, and the speed is rated by the clock frequency, right? So there's an internal clock, like dot 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 dot. So for every pulse from that clock, and the CPU execute one round of command. And for example, like when we write code in C, and if we say like if A is greater than B, so that's like a conditional structure, and which allows you to go in or not go into a certain block of code. So that condition takes 1 clock cycle to compute. And so also an addition takes 1 clock cycle, a subtraction takes 1 clock cycle. But when you want to take a square root of something, and this is actually converted into, I'm just making this up, like converted into, for example, could be several multiplications and addition, subtractions. So that kind of command will take a few clock cycles. The development board has many functionalities, for example, communicating with peripheries, and computing a string, and to kind of append a string to another, and so forth and so on. So at the very bottom, they are all like arithmetic operations, but they were all implemented as arithmetic operations, but it will take many of those operations to execute some high-level functions. So therefore, if you have a CPU with like faster clock speed, then you can execute more commands in the given amount of time. For example, Arduino Uno, its clock speed is only 16 megahertz, but the Teensy has 72 or 96 for 3.2, and 3.5 has 120. So you can see it's already a lot faster. But another factor that determines how fast the CPU is like how many transistors are there in the CPU. Like the more transistors, you can compute more command for each clock cycle. So that's almost likely true that the Teensy has way more transistors than the Arduino Uno chip. And also the last thing is the kind of computing units, like how optimized and those computing units is. Like the more optimized the computing units, the more efficient it computes in a given amount of time or a given amount of clock cycles and with a given amount of total transistors. Okay, so that's a big digression.
Hey Manny.
Yeah.
Just really quickly. So what kind of architecture are the CPUs? Are they ARM? You know.
What's that?
What's the architecture of the CPU? I mean, surely it's not like
ARM.
x86 or ARM. Okay.
Yeah, they're ARM. Yeah, ARM CPU, real-time ARM CPU. You see the Cortex here, right? Yeah. The Cortex series. Yeah, it's funny. We are neuroscientists and we are using a chip codenamed Cortex. But Teensy is a third-party Arduino compatible board. So at the very core, it uses the Arduino library. I'm pretty sure that everybody knows this, but just to make sure, like here in the documentation reference, you can find the core library that Arduino provides to us. So in Arduino, we are programming in a C++ environment, but oftentimes we are not directly using the C++ low-level functions to control the hardware. Like Arduino library has provided us many intermediate level or even high-level functions that solve a lot of problems. For example, digital read, digital write, analog read, write, and serial communications, and setting up interrupts, tone, no tone. I'm mentioning those because we are going to see what I just said later. Okay, back to Teensy. So, by the way, this is a very useful site. I mean, this is something you probably just cannot avoid. So if you search like Teensy in Google or DuckDuckGo, probably this is the first one going on. This is the official website of Teensy, and we are looking at some documentation about the download and install. So here I just want to, I'm sure everyone has read it, but at a certain point, but here I would just want to highlight there are version compatibility issues. So you see like Teensyduino, which is the add-on for Arduino software. By the way, when you want to use this, you first install Arduino, and second, after finishing that, then you install the Teensyduino. So the Teensyduino will look into your computer to see like where you installed it and how you installed it, and then put this add-on to it. So then here, the version 1.53 of Teensyduino is compatible with the following ones. So yeah, just be careful when you choose versions. All right. And then we can go down to the reference on this website, and then let's look at the pin assignment first. Oh yeah, so Teensy has released 4.0 in the 4th generation of Teensy, so they no longer support 5-volt tolerance, but I'm sure the speed is way faster.
Sorry, can I ask a dumb question?
Yeah.
Why is the 5-volt tolerance so important?
Why is it important?
Yeah, 5-volt tolerance. Did I miss something?
Yeah, because many of our peripheries actually operates in 5-volt, so there are less and less of them nowadays. So it's hard for me to think about examples right away, but they are 5-volt peripheries, and when you connect to Teensy, only 5 volt tolerant ones can run those devices. Okay, so here we're going to look at digital I/O, analog I/O, PWM pins, or actually, I think the 3.2 pin now is a better illustration because it has more legends here. So digital signal is or none. For Teensy, O is 3.3 volt, none is 0 volt. So even Teensy 3.2 is 5 volt tolerant, but the signal that the Teensy sends out is still 0 or 3.3. So that's digital pins in gray, and analog pins in this color, but those are analog inputs, which reads a graded value of voltage. For example, you mentioned that you want to use the pulse signal to measure the leaks rather than the electrical leak detection. Then in those cases, you will be using one of the analog pins. But you can see that some of the pins can be digital and analog at the same time. So then that has to do with how you assign the pins in the code, and we'll get there. PWM pins. So PWM pins is PWM stands for pulse width modulation, and it's just a way to use digital output to simulate or to achieve some effect for analog output by quickly turning on and off the digital signal with certain proportions in time. And so if the proportion is high, meaning going up is more than going down, like 1 is more than zeros, then you have stronger overall output. And if the going up is shorter than the going down, then you have an overall weaker output. So this is useful for example, controlling a dimming LED or driving a motor controller to control the speed of motor rotating. So the serial ports are the most important here because we communicate many useful devices using this, which include the Zaber controller. And later in the final example, when we actually get to the behavior code of the sequence leaking, you will see I was connecting the Zaber motor to serial port 3. So by looking at the color, and you see the serial port 3 is over here. RX means receiving signal, and TX means emitting signal from the point of view of this Teensy board. So then if you look from the Zaber motor's point of view, and Zaber controller also have the RX and TX. But in that case, the TX, T stands for transmit, and send the signal out. Therefore, the TX of the Zaber controller should be connected to the RX of the Arduino. And the TX of the Arduino should be connected to the RX of Zaber controller. But one thing I have to mention here is that serial communication is just a protocol. It just it specifies how the signal goes up and down and what information that encodes, but it doesn't necessarily specify the voltage they are working at. So Teensy 3.2 works at 3.3 volt and it's 5 volt tolerant, but it works at 3.3 volt. But the Zaber controller actually uses RS-232, which is operated at a different voltage. Maybe there are other differences. So that's why we use a serial converter to convert one set of voltage signal to one format of voltage signal to another format. So that's the little chip we see between the Teensy board and the Zaber controller.
Sorry, Manny, if I understand it correctly, so the Teensy the job of the Teensy is just to send the command signal to the Zaber controller, and the Zaber controller then sends so does it really matter? So that voltage you're saying, that's the voltage that the the controller uses to control the motors, or it needs to be, in order to read the command signal, they have to be the same voltages?
Yeah, the Arduino only sends commands.
Right.
It's basically send strings of command. It's even human readable.
Okay. Cool. And so for that to be readable by the Zaber controller, the voltage range needs to be changed.
Yes, they're different. So the Teensy's serial port operates at 3.3, and then the other one I think is a higher voltage, and also it's called RS-R232.
Okay.
Standard.
And this is done by the satellite board.
No, so it goes through a little bit of satellite board, but there's no electrical components in the satellite board. It just like go into satellite board and comes out from a wire, and then connected to the Zaber controller via a converter.
Yeah. Okay. Thanks.
Yeah. So serial ports are not the only kind of communication ports, and it's just like even serial port has different like communicating standards, but although the protocol is the same. And we also have like other protocols like I2C, SPI. When are we going to use that? For example, like when you have a analog to digital converter, or a digital to analog converter, or a thermometer, or a barometer, a digital thermometer, digital barometer. So in general, many kinds of peripheries. So one example is what I believe Linhua used to measure the temperature around the tongue. So that board was probably communicating via SPI or SI2C. Okay, so that's basically all we are going to do about the hardware. And lastly, in the COVID time, or even not in the COVID time, we write a protocol. It could be a modification, or it could be a new one, and we want to test it even when we are at home or at lab in front of our computer. And this is a very useful setup. We just have a breadboard here. Maybe the bottom picture on the right side is more clear. So a breadboard or connected only in its own side, right? It's divided in the middle. So then like you solder a row of pins, male pins to each side of the Teensy, and you just plug it in at the middle. So then you can connect from the side to access those pins. And then you can hook it up to many LEDs. And we can say like, let's use this LED to mimic the Q delivery, and use this LED to mimic to represent the water valve opening and closing, and the other LED for something else. So then we can basically test our code, at least test the logic of our code pretty easily. And in fact, if your Q is a flashes of light, and then you are using a solenoid to control the water, to control the water delivery, then you don't even need to change the signal. Like what you apply to these LED is exactly the signal you apply to for the actual visual stimulus and the solenoid control signal. Okay. All right. So then we finished the first part, and now let's move on to the second part, from hello world to task protocols. Okay, so this is an empty Arduino sketch. And so first, everybody knows what's the difference between setup and loop. So the code in Arduino runs mostly serially, and then the code in setup will be run once, as was explained here. And then the code in loop will be run infinite amount of time, and just going top to bottom, top to bottom. So let's first look at an examples. You can find many useful examples from file examples. And the first one is a blink. Yeah, so it's very simple. First, it's just control the LED to turn on and off on the Arduino board, and then a built-in LED in both the Arduino Uno as well as the Teensy series is the number 13 pin. So even without hooking up any LED, you can test some simple functionalities using this built-in one. So we can set up the LED as an output, and this goes to what Will mentioned, like when a pin has multiple functionalities and how do we determine which one to use, and that's done by the pin mode. Right? You can let the 13 pin to be output, a digital output, or I think analog output. But if you don't do anything, I think there's a default option. And in the loop, so just turn the LED on and then wait for 1 second and turn the LED off and wait for another second and looping again and again. Okay, so why am I talking about like such simplest?
Quick question. How do you specify how long the LED stays on?
So using the delay here, right? So this.
Okay. So it'll stay on until, because you need a separate command to like turn it off.
Yes. Yeah.
Okay.
Yeah, I'm glad you brought this up, because the fundamental difference between writing code in Arduino versus writing analysis code, let's say in MATLAB or Python, is that in the latter, you don't need to think about time too much, right? Well, actually, you want things to compute as quickly as possible, right? But in Arduino, it's totally different. So we have to form a new mental framework to incorporate time into our code writing. So when you write, for example, I can ask you folks questions, and you don't have to answer, but you can answer like you can just think if you can answer that. Like, how fast does this line execute? So we said like the code goes from here and serially to here and then looping in here, right? It's in a linear procedural fashion. But when I ask you like how fast this line is executed, how fast this line is executed, and how fast this line is executed. So to be really good at writing Arduino code or this kind of behavioral control code in general, and we have to be clear about those things, right? So but here's a simple answer: like this line takes basically no time and probably a few nanoseconds, and then this line takes a few nanoseconds, or maybe hundreds of like tens of nanoseconds, I should say. And this line takes around 1,000 milliseconds, and I say around because there's a little bit interesting thing in the delay function. I think the accuracy is like plus minus sub-milliseconds. And then this line is executed with tens of nanoseconds, and this line is 1,000 milliseconds. You can just see like all the functions that are not delaying time, that are not explicitly manipulating time, as being executed instantaneously. Just like they take no time to execute. And then, but later, when you are starting to write more advanced code, so you need to think, oh, how much? Well, you may not need to think, but it's good to think about, so that you can make your code more robust and reliable. For example, like forming strings takes maybe like tens of, or maybe some complicated strings may take like 100 microseconds. And then that could be a problem. Why? Because when you are forming a string and then some external event comes in and interrupted the string forming process, or even though the window is only 100 microseconds, but it interrupted, and the string will be formed in an abnormal way. And so actually, this is a kind of known issue that it's not a big deal, and that's why it's procrastinated from fixing it, is that in some of your behavioral data code, and you may see some warnings, is, oh, this message is corrupted, and which shows as a yellow warning. And then when you look at that message, it's a string and inserted by another string or some weird characters. So that's that's when this kind of thing happens. So like if you know that some of the code, some of the process is taking too long, then you have to be careful. You have to protect the execution of that code from other things. So that's a kind of advanced topic, and we'll probably not cover today. But what I'm trying to say here is to fill the time, to go through your code, even the simplest one, procedurally, and along the time axis, and then to ask ourselves like how much time each line is taking, and imagine the flow of time, especially when we are writing a behavior protocol. Okay, this is one reason I want to bring up this, but more importantly, this piece of code is simple, so it's easier for me to demonstrate the added functionality to this simple code. The problem of this is that when you upload this code to Arduino, everything is fixed, right? Yeah, well, actually, why don't I just do that? Yeah, the first time compiling it usually takes a lot of time. And the next time you click it, it will be easier. Just for testing that. See, the LED is blinking at 1 second. But here's the problem. So we uploaded the code to the Teensy, and we just when we plug in the power, we just let it run automatically. And there's no way we can change the way the light is blinking. But imagine if we are running a behavior, there are a lot of behavioral parameters, and we certainly want to change those parameters. Well, while we probably want to change those parameters on the fly. For example, the reward size, right? The animal becomes less motivated towards the end of a session, so we may want to increase just the water reward a little bit just to motivate to keep it going. And that's just one example. So you can write Arduino code using this library to achieve that, but that's going to be kind of complicated. And if you want to do it in a generalizable way, the code will be even more complicated. So for doing complicated things, to make doing complicated things easy, then people come with libraries, right? So what's behind the digital write and delay? They're not complicated, but they're kind of complicated for non-experts, and also it handles a lot of like Arduino versions, like different board configurations and so forth. So like we can wrap it in a library. I'm going to show you another example. So examples for communication and dimmer. Oh yeah, so I just moved the LED one to the right side. So you see here, turn it to 13. This is actually how we write it how we kind of do something like that using all the built-in functions. So LED pin is 13 again, and here we set up the serial communication. So using the serial.begin. So if you want to use serial communication, then you have to run this code at least in setup for once. And the pin mode as before is output. And in the loop, we're going to read what read a user command. Well, in this case, it's just a number from 0 to 255 from computer to Arduino, and then read that command into a brightness, and then I'll use analog write to the LED pin for the brightness. And then the analog write here is actually a PWM signal, pulse width modulation. So let's just upload it. And then now let's open the serial monitor, which we'll look at a lot in the next half an hour or so. The demo wasn't successful, but what it's supposed to be is that when I type in the number like 0, and then the LED will be turned off completely, and then 255 the LED will be fully lit, and then like 100 and at 120 something the LED is like halfway bright. Okay, so I'm not gonna go into debug it, but here just to see how like we can use serial communications to send information between, well, in this case, it's only from the computer to the Arduino and change something from the Arduino. But like I said, when we want to do something more complicated.
Hey, Manny, can I ask you a quick question? So if I understand the code correctly, every time the loop function runs, it checks if the serial communication has been sent. Is that correct? So every time the loop is running, it's checking if the serial input is there.
Yeah.
Right.
Right. So every time the loop runs, are there incoming data into the serial?
I see.
Yeah. Go ahead.
And so the rate of monitoring is given by how long it takes for the loop to run. Is that correct? Like how often it checks for this input?
Oh, the loop runs as fast as it can. And then and then checking whether there are data or not takes no time to run.
Okay.
I think it takes just one clock cycle to check that. Yeah, so basically the loop is probably run, like if we don't type in anything, the loop is probably run like tens of mega times, tens of million times per second. Yeah, so very, very, very fast.
And I don't know if you'll have time to go into this, but what is this number 9600? I mentioned, I know you said something as baud rate or something. That 9600 number.
Yeah. So, like digital signal goes up and down, and it's 9600 is how many times it allows the signal to go up and down. Basically, the temporal resolution of data bits. So we can actually go higher. Yeah. So for Teensy, we just use this almost all the time because Teensy is capable. It can actually go even higher, but all right, we were talking about libraries because for complicated communications, complicated communications require complicated code. And this is going to be very useful if we put those complicated code into a library and only expose like simple functions for users to use directly. And this is what I did, and I wrote the Satellites library. And you can find everything about the satellite system in our GitHub repository, the Satellites repository. And you can see the Satellites viewer, Satellites shield. But here we're going to look at Arduino libraries and satellites. So later, the Zaber motor is something you also want to have. And if you're using my rig or you want to write something similar for your rig, many rig is also, we'll get to that. And so how to let Arduino know that we have like third-party libraries? We just copy this folder, this satellites folder, into a document, Arduino libraries. So here I already have this. Next, we'll go through the 4 examples here. And for each example, we will learn something about the functionalities in this library. So we begin with SatellitesBlink. Yeah, so on the right-hand side, you see it's the Arduino official example Blink, which doesn't give us any way to control like the time the LED is turned on or the time the LED is turned off. But here we are going to change that. So we'll be able to change both numbers. So when we are using a third-party library, we first need to tell the code we are using them, and by the # include and satellites.h. So the satellites library comes in the form of a class, which is the satellites class. And for those who are familiar with object-oriented programming, and like class is just a convenient variable that includes a lot of related functions. In OOP, is called methods. They're basically the same thing, and as well as many property, some related values about this object. So, and then as in the global variable, we create a satellite object. I just named it SatellitesRead SR LED pin 13 SP4. Since we are going to change the delay, so it's better to make them some variables, so we can change those variables. So LED on duration, LED off duration. And we set up the serial communication because satellite system is based on serial communication, so we still need to enable it, and the pin mode. And we'll skip that for a moment, and let's look at here in the loop. It looks very similar, right? This is right, like turn the voltage to high and delay for this period amount of time. Turn the voltage to low, delay for this period amount of time. Okay, so how do we interface with this?
Can I ask a question about the setup actually before we go forward? So how do you decide what, I guess, what needs to be done inside the setup loop and what can be done outside of either of the loops? I guess I'm wondering. Like initially.
I see. So what needs to be done inside the setup and what's in the loop?
Or like above setup?
Oh, so first of all, setup and loops are functions, right? Yes. And then outside those functions, we declare variables, like global variables. In C, C++, there's a concept of global, the scope of different variables. So, for example, like if I'll just going down here, so you see like this is a function called myReader, right? And then inside this function we have 3 variables, and this variable will not be available or accessible from outside that function, right? Same for loop. If you create anything here, it's only going to be available in each run of that loop function, and same as setup. But those outside, so you can access them from any function.
Yep. So I guess if I initialized a variable inside of setup though, then I wouldn't be able to access that anywhere else. That may have been something that I was doing wrong.
Sorry, can I say it again? Like I'm hearing from my phone, so this sound is pretty low.
So I guess something that I might have been doing wrong in some of the functions that I wrote was initializing variables that I needed to use inside of setup instead of globally.
Oh yeah.
Okay, cool, thanks.
Oh, was that a question? Or
I was just thinking out loud about what my mistake probably was.
Oh, okay, I see.
Yeah, I mean, maybe this is kind of an irrelevant question, but what is the added benefit of running line 34, 41, and 44 in the context of a function as opposed to just like running it outside of a function?
So you cannot run functions outside of setup or loop. So you can only declare variables outside.
Okay.
Yeah, but now executing functions outside.
Okay, cool.
Yeah.
Thanks.
Okay, so so far we just talked about the part that that's the same as before, but now we are going to look at a serial read command. So previously, in the dimmer example, the Arduino built-in example dimmer, we use like serial read to read some number I type in, and then read that into a variable, and then apply that variable to the brightness of the LED using the analog, right? But here we want to write something more, read something more complicated. We want to read a command, and what kind of command? A command like the LED on time, and we want that to be, let's say, 200 milliseconds rather than 1 millisecond. So this, some complicated command like this, or LED off time, let's say like 3 seconds, yeah, something like that. And here we can use the serial read command function. So then where does this function go? This function here invokes a function that you choose to invoke. And here we choose to invoke the function called myReader. This is a user-defined function. Before getting into like the details in here, so we just want to be clear that myReader just handles all the incoming command. But so far, myReader is just a random function I might kind of put at the end of the program. So we have to let the Satellites class to know that we want to use this function as the reader function, which the serial read command should call. And we do that by the line 44 here, sr.attachReader. So like, and then put the function name here, or it's called a function handle here. Okay, but just to make sure we are 100% clear, I will just go through it by time again. So first include that, include the library, and initialize the creating a satellite object and other variables. And in setup we run once, we have to enable the serial communication by serial.begin with a value like this, and then the pin mode, and we attach the reader. We tell which reader we want to use, and in a loop we just keep reading that, keep reading that, keep reading that for every cycle of the LED blinking. Okay, so how to read the commands. And so, but before reading, let's design the command we are going to read. Satellite library has this, well, I should say satellite system has this required format, or it has its own protocol of communication. Protocol is just the format of information. So here, I want to design the following command. Well, it could be this, but what's in the code is like on duration, like some number, and then off duration, and also some number. And then you can actually see the, oh, okay. Yeah, so we can say like on duration some number 1, 2, 3, and then off duration 4, 5, 6. But we may also want to assign an on duration and off duration at the same time in one command. So then we can do like we can create another command called on off duration 1, 2, 3, 4, 5, 6. And the first number is on, the second number is off. And we can also say pause 5 seconds. It just stop executing. And this command doesn't require any number following it, right? It just pause 5 seconds. Yeah, so with this in mind, let's just see how to implement this. So, okay, here is the main message. So the format of a command is basically a one-dimensional array, right? So here is the one-dimensional array with 2 elements, and with 3 elements. And then for each array, the first is always the name of the command, like including this. So this is a 1-element array. just only the command like called pause space 5 space sec. And then this is the 0th position, this is the 1st position, and this is the the 2nd position. Like we are doing 0 based, and this is again, of course, the 0 position. Okay, back to this part, and let's just go in time. So first, we can get the command name, which is in the first place called sr.getCommandName, and this variable will be storing this part, or this part, or this part. So then we can get the index of the current read, and okay, sorry, just go back one step. So the myReader function read one command and one position at a time. So each time the code is run from the beginning to the end, it handles one position of the command. And the next time it's run, it handles the next position. And then the next command, the first position, next position, and first, next, and next, and first. You see, so myReader doesn't digest the entire message at once, but like only one position at a time. So therefore, we need actually 3 pieces of information. So first is what is the command I'm reading, right? So then this is done by getCmdName. You know, like here, when I'm reading this command, even well, if I'm reading the first position, the command name is onDure. But even when I'm reading the second one, the command name is still onDure, right? It's the same command. The second piece of information is the current index. So when we are reading this, the index is 0. When we are reading this, the index is 1. So it's the current index. And of course, we also want to get the value, right? So when we are reading the first one, the value is actually just 0, because there's no value, we just put 0 to it. Then when we're reading the second part, the value here will be 1, 2, 3. Okay. After that, they're all just standard programming, like many if, else if, else if, else if conditions. So for example, if the command is onDure, and also if the current index is 1, which means we are reading this number, right? So when we are reading this number, the command name is onDure, and then the position here is 1. Then we assign the value to LED on duration. So then we'll be assigning 1, 2, 3 to this variable here. This is a global variable we can access anywhere in our code. And similarly, when we are reading this part, and it's in the offDure command, right? And it's also at the first position, counting from 0. And here is the on-off duration command. And when the index is 1, which means we are reading this number, and then we assign this number to LD on duration. But here you see, this part is the line 114 is almost the same as the line 108, and the only difference is that here we require the index to be 2, which means we are reading from this value 456, and when that happens, we assign that value to LD off duration. And lastly, so we have the pause 5-second command, and here you see the index is 0, because it doesn't require any numbers. So whenever we are running this, then we can do the following. Whenever we are running this command, and at the beginning, so we can do the following straight away. Okay, so let's see what happens. But what I'm gonna do right now is I will just like click on duration, and then I turn it to 200, and then off duration some number, and on off duration. I'll just try these few things, and I'll show you how it changes on the screen. Well, how it changes from the LED here. Okay, so in my serial monitor, so click on duration. So you can see from the code, the default value is just like 1 second on and 1 second off. And here I say on duration 200. This is a short on and a long off. And then I'll just try the on off duration. Remember, this command requires 2 following numbers. So basically, we are assigning the on duration and off duration in one command. And here I'm using 100 milliseconds on and 100 milliseconds off. So it's supposed to blink 5 times a second. Yeah, it's doing that. And then lastly, I will just write pause 5 sec and hit enter. And it is pausing for 5 seconds. Yep, that's a demonstration. By using the Satellites library, it's kind of easy to design your commands. So it's actually very important. Like, rather than directly jumping into the nitty-gritty of like the code, why don't we just first write out the command, the kind of command we want to use to control the parameters in your code, and then while looking at these like design command, then we try to write like how to like implement these, like what command name it is, and what is the position of this variable, and then we can like write conditions to handle each case. And lastly, I just want to be clear that you don't have to write everything in like encrypted acronyms like this, right? So you can even write like pretty straightforward human language, or you can even add like the random symbols to it. It will handle all those. Well, with some exceptions. So for details, you can see this like this inline documentation. It actually describes basically what I said in a more formal language, and also highlighting something that it doesn't accept. All right.
Oh, I have another question.
Yeah.
I'm not sure when it would actually be useful to do this, but is it possible to change what the delimiters in your serial commands are?
Oh, yes, you can. Yeah, so in the SR class has a property, and then the property has a delimiter property, and then right now the property has a value of comma, and you can change that to like $sign or whatever symbols you like.
Cool, thanks.
So far, it's one-way road, right? And we just write in something like pause 5 seconds, and then while the device pauses, but we don't get any feedback from the serial communication, and which we want to have. When we are dealing with a behavioral task, we want to change the parameters, but more importantly, we want to collect data, right? So what's going on there, and what's going on with the animal? And when we apply a command, we want to know, oh, the value is the command is actually executed and the value being changed. And now let's move on to called SatellitesBlinkData, meaning we are actually collecting data this time. Almost everything else is the same. But here in the loop, you see after we turn the voltage up, which means when we light up the LED, and we send a message to our serial to our computer. We set LED on, basically just notify us the change of status, and we delay for a while, and then turn the voltage down, and we send the data LED, send the message called LED off, and we can see what's happening here. Yeah, so you see something interesting, right? Like the LED, we only send the message LED on, but the LED on is also always followed by a number automatically, and as well as LED off. And actually, any string that we send using send data will have a number appended to it, and this number is time in milliseconds. It is a machine time for an Arduino, like counting from the time it's powered on. And you can see this is very important for us, right? When we run a behavior, we want to know exactly when a leak happens, and we want to know exactly when the water is delivered. And so that's why when you use the satellites.send data, the time field is always present there, is required. But we can do more than that. Let's come to
that's machine time since you powered on the Teensy, is that right?
Yes.
Okay.
Yeah. So sometimes you see this number is like it's huge, right? And because we just turn it on and never turn it off. And then so Teensy has a maximum time count. After it reaches that maximum number, it will go back to 0 and counting again. But that number is like pretty big. Okay, so come to my reader. Everything is the same. So we have on dur at 1, off dur at 1, on dur at 1 or 2, pause for a few seconds. But the difference is that now we are reporting back. For example, for on duration, we send a value and it reports a value back, like LED on duration. Okay, I'll first demonstrate that. On duration, let's say 2 seconds, and you'll see the feedback here. So LED on duration, which is, and this is the time, and here is the value which is set in. So how was this message generated? It's generated by the line 89. You see, instead of just sending one command or one string, and we are sending back like 3 pieces of information. So the first is, of course, the string, and the second is using an Arduino built-in function millis. So the millis basically return the current machine time. The current, by saying current time, I mean the time you are calling this function. But of course, you don't have to call this function right here. So you can call a function somewhere else and then report it later, and then save it to a variable and report it later, right? Which we'll see this way of using it later. And the last one is the same. LED on duration is a global variable. It's just basically what's the number here after we have changed it. And you can see like this is a pretty useful feedback, right? And then also, when we do that, the system actually logs when we change that parameter. So yeah, so same for off duration. But here I want to show you something different when we do the on-off duration. So on-off duration is a single command that changes 2 parameters, right? Changes 2 parameters. So then this command will be read 3 times, right? The first here, and then here, and then here. So when it's reading here, the index is 0, and we don't write any conditions to handle like index 0 for this command. So, but we do that for index 1 and index 2, which is here and here. And but I just want to have one feedback for the whole command. So that's why I don't write anything in this condition. So in here, we don't write any feedback. There's no send data. And we only send the data back in the second command. But in order to put both the on-off durations in one command, we have to use an array in C++. So this is the one way to initialize array. So it's a duration array here, indicating it's an integer array. And then the first element is LD on duration. The second element is LD off duration. And let's also specify like how long this thing is. You know, like C++ is still a relatively, C and C++ is still a relatively low level language. So it's not as smart as like Meta Python, which kind of figure out a lot of data structures for you automatically. So here you have to tell that this array is like 2 element long. And then, so here we see like 4 fields, right? Instead of 3, and also instead of only 1. So the first is the name, the second is the current time, and here we put the array here. And the last one is telling it like how long the array is. And let's see like what the line 112 actually generate. And I'm going to send this command, and you'll see what pops out. Yeah, LD on-off duration is the current time, and indeed it becomes 1,000 milliseconds and 2,000 milliseconds.
Hey, Manny, can I ask a question?
Yeah.
So it looks like you're using the same function send data,
yeah.
But the 2 times you call it, you're sending different numbers of like parameters.
Yes.
So
yes.
is C++ pretty like flexible that way, or do you have to do some like fancy code to have 2 different function definitions?
No. Well, actually, let me get back to that later. So okay. Actually, later, I in the sequence leaking protocol, there's a use about this, so we can talk about that there. But the short answer is yes. Okay, so lastly, pause for 5 seconds. But the thing I want to do here is I want to report the time when the pause starts, but I really want to send a message after the pause has been done. So you know there's a difference between the time we want to report and the timing we report it. So here's how we do it. So we create a variable to store the current time immediately after the Arduino received the command. And just this is kind of important. Let's just form a habit of saving all time information in unsigned long integer. So this makes sure like no matter how big your time is, it's not gonna be overflowing. And we again delay for 5 seconds, which is 5,000 milliseconds, and then we send the data. So the pause began at this value, right? And here's the timing. Here, let me show you the timing. Pause 5 sec, and I hit enter, and you see like it paused, but there's no message going on, and then it shows like pause began at a previous moment in time. Yeah, so this can be handy. All right, so this is the SatellitesBlink data, and now I'm going to move it to the right side, and then move on to the first kind of protocol we actually write. Okay, so include created a satellites class, But now we have a few more global variables. Those we have a lick pin, which detects the digital signal of licking, and we have, instead of an LED pin, we have a valve pin, which controls the opening and closing of the water valve. And water duration is the time the valve opens. But yeah, the licking text is the simplest, but we don't want to make it too simple, so we have an ITI during which the animal has to wait, and then we require the animal to wait, and we can design it in a way that if the animal licks, the intertrial interval get extended by a period of time, which is, let's say, get extended by the no lick duration amount of time in milliseconds. And its training is a flag. We'll see how it's useful in a moment. Setup is the same. Start serial, configure one pin as input, one pin as output, and attach our reader. I'll come back to this later. This is actually pretty important. And in a loop, so we see there's only one line, which is a read command. So then how come it only has one line? So, like the serial read command invoked the function myReader. And myReader, at the beginning, we just always get this 3 pieces of information. And here, I'm not going to go into the detail, but those commands are just like different commands to change the corresponding behavioral parameters. For example, like WAT changes the water duration, and here we just showed how we can send a feedback message. But what's special is the first command, LFW. So here it executes, instead of changing any parameters, it executes a function. And the function, we can find it down here. And inside this function is our protocol, is our actual, the code that controls the licking. Okay, so then how is the code executed? So like when it's running, that the loop is being looped. Well, the code in the loop is being looped continuously, but most of the time there's no incoming command, right? It's just passing by again. But once we type in LFW, and then like the code goes into the if condition and then start running this function. Inside the function, we notify that the session has started, or lick for water starts, and we set the training flag to true, and then store, and we will keep track of the number of trials, so that's why we can create a variable here. And here you see another loop, a while loop, right? As long as we are in the training mode, this loop will be executed again. So each time it's run is basically one trial. And at the beginning, we increment the trial count, and then we report the time of trial start, and as well as the number of current trial. And we delay for an ITI, and we delay for ITI duration. So this is basically implementing the ITI. But here you see, in the Arduino built-in examples, they only have the delay function, right? But here we are using the satellite object dot delay. So it's actually a method in there. So what's the difference? So the difference is that in the normal delay, there's nothing being done in the meantime. But in this delay, during this delay, this function will be executed, but well, not here, not this line in the loop, but like the same function, which you can now see like behind the scene, will be executed again. Meaning, when you are changing a parameter during this period of time, and the parameter can be changed, so the reader, because the reader is being executed, and so this is a required ITI, and here we have a delay continue. So what is the delay continue? It means like the delay will be continued by this amount of time if this is satisfied, if this condition is satisfied. So then what is this condition? So is lick pin high is actually a function down here. And in this function, it only has one line, which is to decide whether the current lick pin has a high voltage or not. And if it has a high voltage, it means the animal is licking on it. And if it doesn't have a high voltage, it means like animal is not licking on it. So therefore, if the lick pin is high, if this condition is satisfied, then the delay will be continued by this amount of time. And then if during this amount of time, this becomes true again, it will extend by yet another this amount of time. So so you see, this function basically implement the idea of like continually delaying given certain conditions. And after that, and we can wait for a lick response. Right? So here, wait for the animal to lick. So here we have, which is the opposite as the delay continue, right? So the delay until is like will stop delaying if this is satisfied, but we cap the maximum amount of time that we wait by this number. So if the animal just is not licking like forever, like this line will be passed after like 10 seconds in this case. But if the animal licked within this timeout limit, then it will also pass. But the difference is the return Boolean variable is different. So if the lick pin is high, the return variable will be true, and if it has to reach the timeout limit, then the return variable will be false. And if it's licked, which is this variable, then we just control the valve opening and then report the opening time. And here you see like we are using the same trick I showed you in the last example about the pause for 5 seconds. So here we record the time first. And then when we report it, we report both the time when the valve is opened, as well as the duration that the valve has opened. Right? You see, this is the current time, and the current time minus the previous time is basically the duration. And you see, like when I click on this right bracket, it shows where it begins. So it's in a while loop, right? So this is basically a trial getting again and again until we pause it. But once we stop it, then we are going out of the while loop. And then after a report of the session end, it goes out from this function.
The serial read command would only be continuing to execute during the delays, right?
During these delays, right? Including this and that and that. Yeah.
Okay, cool. And then only those 3 locations though?
Yeah. And having these are all the reasons why we can still change the parameters on the fly.
Mm-hmm.
All right, so this is the lick, and then last example before we move on to the actual sequence licking code. But you see, like once we get here, we have actually explained a lot of the sequence licking code. So the first thing I want to highlight is we have multiple tabs here instead of just one tab. And there's really nothing fancy about it. So here you just click this little arrow, and then you create a new tab, and then you just keep writing code. And then in terms of, and when Arduino executed, it just combined all the tabs into like one long code, and then executed from top to bottom serially. And then breaking this up into tabs is really for the viewing purposes, so we can like compartmentalize our codes to make things easier to see and find and read. Here we have a lake for water protocol, exactly the code that we saw in the last example. And here we have a detection protocol, like it's a simple detection task. And I'm not going to go through this. You can try to read it on your own. It's not that different from the lake for water protocol. It's just the logic is slightly different. So here I put the reader in a separate tab, just for clarity. Yeah, one thing I realized I said important, but I forgot to explain in the previous example is this. So in the setup, we attach, so there's a line 46 says attach interrupt and so forth and so on. So we know Arduino code runs serially, right? One line after another in a procedural way. But that's not ideal in some circumstances. For example, like we are executing the behavioral logic, but then the animal licked, and then we want to capture that lick and then report that lick to the computer because that's the important data we want to keep. And how can Arduino just jump from one task to another and then back? And then there are several ways to do it, and one of them is called external interrupt. So the name is straightforward to understand. External means it's coming from the outside, right? The animal licked that triggered a voltage change in a digital pin, for example. And interrupt is in terms of interrupting what the Arduino is doing right now. And then Arduino needs to execute interrupt function. And then after finishing the interrupt function, then goes back to where it's left and then continue. And this is the Arduino built-in function that set up this kind of external interrupt. So the first is the pin we want to trigger the interrupt from. So this is, but you know, Arduino has different naming schemes for the pin numbers. Like from the interrupt point of view, they have like the interrupt 0, interrupt 1, 2, 3, 4, and which are not usually the same as the pin 0, 1, 2, 3, 4. So and then to convert the pin numbers to the interrupt number, and we use the digital pin to interrupt function to do the little conversion. And then the second argument for this is what function do you want to execute once the interrupt happens? And here down below, we have a report lick function. So every time the interrupt happens, we just execute that. So here sr.sendDataLick. And then the third argument is at what condition should we trigger the external interrupt? And here is like when the voltage is rising from low to high at the rising edge. Whenever that edge happens, we run this function. Well, I should say, whenever the edge happens at this pin, and we run this function, which is this, and send the data lick. And remember, when we kind of use this function this way, it will append the current time automatically. So it was in the command window, in the serial monitor, you will see a lick, comma, and number, which is the machine time. So now I have 20 minutes. I will see how much I can go through the sequence licking task in 20 minutes. First, there are many tabs, and then those are just different protocols. And today we'll be focusing on the protocol QP. Okay, but still, let's start from the main tab. So here we include satellites, but as well as many rig, Zaber motor, and servo. So in the handout, I posted several links to the additional libraries we use. I guess I'm not going to get into them for the sake of time. Okay, I will skip those part. Okay, so next, the global variables. So you see here we have way more global variables than before. Well, maybe not crazy way more, but there's actually a lot. So we create a satellites object and also a rig object, and a Zaber motor object. And this is important. Unlike other objects, so here we are passing a parameter here. So we are telling the Zaber motor object we are going to use the serial port number 3 to communicate with it. I'll skip that. And an interval timer object. So this is this handles some timing related things. I'll explain later. And protocol ID, which protocol we are using, and whether we want to pause the protocol or not. And this is a Boolean variable for checking on the fly. Like count, position list, and a special variable or an object called position list. So it's a list of variable type position. And okay, position is another class that I wrote to streamline the conversion between a Cartesian coordinate and the polar coordinate. So remember, the Zaber motor is a 2-axis linear state, right? And the natural coordinate that it operates in is a Cartesian one. But for the sequence leaking, we see the root of the tongue as the center, and then it kind of reaches radially to different directions. So when we can program the behavior, it's easier to use the polar system. But instead of converting, like for complicated code that we want to use again, we want to put them in libraries. So basically, this position is a library, or is also a class that handles this kind of internal conversions. So we'll be using a lot of positions, like this here. Like we're using 7 positions, but we don't necessarily want to limit ourselves to 7 positions. So here I'm creating a position array of length 32. So I mean, you can increase the number to a much larger one. But here the code basically support up to 30 different positions. And here I also set a resting position. So like when the task is done and where we should rest the port to. Oh, the L here means this is a long integer. So a data type issue. And I will make the sequence to be 2. There are 2 sequences in total. And then each sequence has a maximum length of 32, although we only use up to 8 in the backtracking sequences. But here we allow it to be 32. And here you see a 2-dimensional array, right? So this is the C++ way to initialize a 2-dimensional array. So it has 2 rows and 32 columns. What are the numbers stored in this array? So it's basically the indices of positions. So it's related to this variable. So for example, like here, the position may be storing like here, there, and like 6 different positions. And here we can index them, say like from 1st position to 3rd position to 2nd position to 4th position to 5th position, and so forth and so on. So what's stored in this variable are indices, right? So sequence position indices. And the indices refers to the actual positions stored in this array. Frame rate 400, and here is another object intertrial interval, which has many useful, convenient methods that generates a fixed and a random intertrial interval for us. So again, it's encapsulating some complicated code, not so complicated, but like encapsulating some calculations. And here we just have a bunch of time or timing variables. Optogenetic part, we have 4 conditions of optogenetics. No optogenetics, init, mid, and const, and we are again storing them in an array. All right, setup. So what's different is that we not only initiate the serial communication with computer in line 47, we also start the communication with the Zaber motor. You see the serial 3 begin. and attaching the reader. And this is the lick port external interrupt as before. And here is something new. Here is the initialization or setup for the Zaber motor. So Zaber motor stage is the object. This is the Zaber motor object we created up here, and it has many properties and methods. So here is the property is the reverse, whether we want to reverse the direction of the axis. Where's the reference coordinate for the first axis, which is the AP axis, and what is the reference position for the lateral axis, which is the second axis. So here, the second axis in our rig has 5 centimeters long, which is 50,000 microns. So I'm setting a reference halfway, meaning like when we say 0, like the lateral stage is center. And when we say positive, it will go one way. We'll say negative, it will go the other way. I'll skip the jitter. So the maximum speed is this, and then the acceleration is this. So when you feel like the lick port is not fast enough, you want to change the acceleration, and well, maybe sometimes as well as the maximum speed, and acceleration is more important. But when you realize that the port is sort of slipping, right? The driving force is not enough to keep pace with the intended movement. Then that means it's being overloaded. Then you want to like decrease the acceleration. I'll skip that. And here I'm instructing the lick port to move to the resting position here. It's just like the safe position far back. And here we just want to initialize some parameters. So it's not like directly related to the lick port stage object, but it's related to the position list. So here I'm just using a loop to assign every single position variables to a kind of say the same position. It's really just for safety, and also for sequence. I'm initializing all the sequence index to 255, which is like nothing, because our position list length is only 32, and this is certainly out of range. So all the initialization here is just to prevent accidental control, like to move the port to an unexpected location and therefore damaging it. All right, in the loop we have our old friend serialReadCmd, and which will go to the reader function. But here I kind of pulled out the protocol selection from inside the reader function to the outside. To choose which protocol is determined by the protocol ID, which is a global variable. And of course, as you can imagine, we can change the protocol ID in the serialReadCmd in the reader, in one part of the reader function. Right? So, well, just to show that, yeah, you see over here, whenever we have the PID command, and it will assign the first value to protocol ID. And then if we type PID, 3, it will go to quantum pursuit function, which is the main thing we're going to talk about. First, these are just some local variables we'll be using. This is a while loop, while true, and meaning like what's in here will be executed again and again, just like what we saw in the simple licking protocol. I'll go through this page in several passes, and each focusing on different aspects of the code. So the first is the timing. And for the timing, we just want to highlight some key functions. So here you see like delay and delay continue and things like that. And that's basically like waiting for the animal to stop, right? And then delay continue or condition is lick behind, just like the examples we saw. And then we extend whenever the animal licks during that, period, then we extend by this amount of time. And then where are these time, right? So you see the ITI is an object, is from the intertrial, well, not intertrial, it's from the interval object. And then this provides us with some like handy ways to generate, to store the fixed duration as well as generating a random duration. And the generation of or refreshing of these values were done at line 30, right? ITI next random. So it will give us a new randomly sampled ITI. And we are basically using it over here. And then reporting some information about the ITI, like how long it actually ended up taking the animal to start the next trial. And here the trial starts, and then we present the queue immediately. After the queue, so we'll see if the animal like licked, or there's a timeout, like when the queue, after the queue happened, the animal just never licked, and then until it's just automatically, until this trial is just automatically aborted. But let's say the animal actually started licking and the trial was not aborted, and then it goes into here, right? And then now we are going to iterate through the positions. I imagine we have the 7 positions, but it can be any kind of positions that's stored in the position list, right? Well, also in the not in the position list, in the sequence lists. But this is not the focus. The first focus of the first pass is the timing, right? But here is the loop. So sorry, here is the loop. Wait, oh yeah, here, yeah, from here to here is the loop, is looping, iterating through positions. And after all the position was looped, and then we have the water delivery here, and here we have a delay of water. You know, like there's a delay before the water is started being delivered, and then now we deliver the water. You see, like here I'm calling the rig class. This is again just for simplicity, for making the code concise. So here we are passing the water duration to this variable, and inside another variable in this method, and inside this method, it will do like digital up, digital write high, and then pause for this amount of time, and then digital write low. It's just a one line. I just made it into one line here. And in the end, there's a drink duration, and after that, let's go back to the while true and ITI again, and then that's the next trial.
Hey man.
So this is yeah.
So when the trial loop is running, the only difference between a standard sequence and a backtracking sequence is, I guess, the pause IDX variable that's going to be different. Well, not pause IDX, SIG IDX is going to be different.
Yeah, yes, a SIG position indices. Yeah.
Okay. And so where is that chosen at the start of the trial, like whether this trial is going to be a standard or a backtracking sequence? I might have missed that.
Yeah, whether it's, so you see, we at one time we only store, so you can write it in many ways. The way I wrote it is that the number of sequences we store is always 2. And then
right.
between the standard and random sequence, actually the computer updates the sequence. The computer sends what the next sequence to be.
Right.
Basically overriding this variable for every trial.
I see. So that selection is not done at the Teensy level. That's done.
Yeah, it's not done at the Teensy. It's done from the computer. Here, I'm glad you brought this up. I'll just quick. I'm not going to get into this, but I will just show which command it is. You see, here from line 102 to 111. So the command is 60.
Gotcha.
And
Got it.
yeah, just assign a series of numbers into this.
This is
But
where it's
here
reading the sequence command basically from the computer.
Yes. And here you see, like, this is a fancier way of like doing the condition on the indices, right? So rather than index equals certain value, here we see that if the index is in certain range, right? So so the actual command is like 60, comma 60, comma 1, 2, 3, 4, 5, 6, right?
Cool.
Oh, sorry. Yeah.
Yeah.
0, 1, 2, 3, 4, 5, 6.
Got it.
Yeah.
Thanks.
And then you see this is the first place, second index, third index, 4, 5, and here it's all fall into this range. And when it's in this range, and we use the indices to change the corresponding element in that array, in the sequence position indices array. And here for sequence 1 command, the only difference is here. So here we are changing the indices in the first row, and here, well, in the 0th row, and here we are changing the indices in the first row. Yeah, so this is the first pass, and the second pass will be focusing on the control points. So the control points include here. So while the protocol pause flag is true, and it will just keep delaying until we set the pause flag to false. And what is the pause flag? Is the it's a PPF command. You see, whenever it receives the PPF command, it just negates the current protocol pause flag from true to false or from false to true. And that will affect whether the program will be stuck in here or get through here. And protocol ID, if we kind of in the reader we can set it to 0, then we'll break out this loop. Then we basically terminate the task. Yeah, the other control point is over here, right? So here is lick or abort. Again, delay until the first argument is a function, right? And the function is defined not here. Utilities. Yeah, it is. So the function is here. So it's checking a condition returned by this function, and this condition has two parts: whether the animal licked, or if we have set the protocol ID to 0, right? Meaning it, or we want to terminate the task. And similarly, over here we have another control point. It's like it's lick or abort. So normally, if the animal licked, it just go through the next position, and or if we just abort the trial, it will also go to the other position. And then after all the position is run through, and the trial will be aborted. This is our second pass, which focused on control point. And now we're going through these code in the third path, but this time we are going to focus on the triggers. Okay, so the first trigger is during the ITI. Yeah, it's over here, line 33. So this is still during the ITI. This is actually the beginning of the ITI. And here we turn this pin, the camera pin, to high. And what does this pin do? This pin opens a video file. So this pin is connected to the National Instrument Board on the high-speed video computer. And when the signal through that line get turned from low to high, then it opens a new video file, or it prepares a new video file. And the second trigger is the time when the trial starts. We need to synchronize the video, the Arduino, and the Intel and other recording systems. So here we are like leading a digital output out from Teensy connected to Intel. connect to the digital input of intent. And at the very moment of the trial start, when we kind of report this trial number, and we create a pulse, we create a square wave to intent, and the width of the square wave correspond to the trial number. So if we are on the first trial, the pulse width is 1 millisecond. If we are on the 500th trial, then it will be 500 milliseconds. So this is what the pulse on function is doing. It just create a pulse. But the little twist about this is here we want to do this in a parallel way, meaning we want to create a timed pulse with certain width, but we don't want that job to block us from executing the rest of the trial, right? We don't want to delay the trial. So in that case, we need to parallelize that processing, and this is done by some trick inside this function, and that's also why we need to create this class, the num timer. It basically allows for a kind of asynchronous operation or like parallel execution about time. And so this is okay. Next, this is a misleading function. So this is actually a non-MATLAB, the Arduino built-in function. It uses a digital pin to create a vibration, a sound. So basically, it's called tone because like people use it to connect it to a little speaker and playing some buzzing sound. But here we are basically using it to create a fixed frequency pulses. And so what is the frequency? It's a frame rate. And then which pin we are sending that pulses out is the frame pin. So the frame pin actually goes to the back of the camera and triggers the capture of individual video frame. And the frame rate here is 400, which is what I use. And the next trigger is a queue. Yeah, present queue. So here trigger queue. This is another sort of big topic. I'm playing the sound using the Teensy audio shield. So the trigger of the queue is actually just a pulse, just a TTL, and that goes to the audio board. And the audio board has its own set of like preset parameters and logics to play that little beat. And the audio board is also responsible for mixing that the sound of Q with the sound of white noise, as well as the sound of pre-recorded noise of the movement of the linear stages. So we'll get that in maybe another day. Okay, so those are all the triggers, and then you may say, oh, like what about the Optogenetic trigger? So I will get to that last. Okay, now let's focus on this. So we are getting close to the end. Okay, so let's focus on this. So this is looping through positions, and I just want to highlight here. So in my task, if the two position, from the last position to here is adjacent, then the lick port moves in a straight line. Like position difference is whether they're adjacent or not. And if the port position from the previous to the next are not adjacent, then the lick port moves in an arc. So this is related to the backtracking sequence. Right? Backtracking sequence doesn't move to the adjacent one. That's why it moves in the outward arc. Also, based on the difference in position, we have a different refractory period. So refractory period is like when the animal triggers the movement of the port, like the port will not be triggered within a certain period of time. So this is mainly to avoid like some detection artifact, like the same leg actually trigger like multiple rising edges in the electrical signal. So this is basically avoid that. This is what I want to talk about, like inside the loop, some details. But you know, like the sequence actually changed from one to the other from one trial to the other. And this little part here is how we kind of go through individual sequences. Like, so every time a sequence is executed, the sequence ID is incremented. If the sequence ID is greater than the total number of sequence, we kind of run it back to 0, to go around it back to 0. Okay, so lastly, optogenetics. So during intertrial interval, we compute what is the opto condition is going to be. Sorry, not here. Yeah, over here. We're going to compute what the opto type is going to be. And then here we have a list or an array of optogenetic probabilities, like 10%, 10%, 10%, 70%. And there are 4 options. So then the choose function just use some random number generator to randomly sample like what the condition is going to be. And based on this condition, and if the opto type equals 0, then we trigger opto at the Q. And if the opto type is 1 and the current position is the mid sequence, it's a 4th leg, which is the opto step equals 4. And then we trigger the opto at the mid sequence. And here's water delivery. And if the opto type is 2, which it means the water delivery, and it triggers the optogenetic stimulation. And of course, then what happens if the opto type is 3? The condition 3 is just no opto, so there's no need to handle that. All right, so we have finished the sequence leaking protocol, but you can see, like, for example, trigger opto, LickPort move, LickPort move arc, those are just functions, right? So here, let's just get to the bottom a little bit. I will just quickly go through them. So report lick is the callback function, or is external. It's the function that the external interrupt calls, right? And here is a little bit more complicated. So here, when we attach the interrupt in the setup, instead of saying rising, and we say change. So meaning this function is called both by the rising edge and by the falling edge. And the rising edge indicates the touch onset, and the falling edge indicates the touch offset. But how can we distinguish the 2 conditions in one callback function? This is how we do it. So when the external interrupt happens, and we can check whether the lick is, when the lick pin is high or not. If it's high, then it has contact. So then we report lick on. And otherwise, we report lick off. And its lick pin high is here. It's basically the same. And its LickPort board, we talked about this. And its LickPort move X and LickPort move Y are encapsulating a command that moves move the 2 axes independently. So LickPort move X moves the first axis to this value in microns. And LickPort move Y moves the second axis, which is a horizontal axis, to this position in micron. And LickPort move. So there are 2 functions called LickPort move, and the C++ distinguish them by their different input argument. So position. So LickPort move and LickPort move arc actually moves the 2 axes in a coordinated way. Okay, going down, number pulse on is the one I mentioned that uses the interval timer to send the trial trigger. Number pulse off is a function used in the number pulse on. And the Q trigger is this. You see, like, even in these utility functions, the function is further wrapped up in the rig class. But you certainly don't have to do that. You can simply just use like digital high, digital low, and some delay and things like that to finish all the works. And here I'm just writing it in this way for conciseness, visual conciseness. and trigger Opto. And here we do two things. So first, it send a TTL to wave surfer, WS pin, wave surfer pin. And this is the duration, 1 millisecond. And then we report like, yeah, we send the Opto at this time, the current time minus 1 milliseconds. And then what is the Opto ID? Is it init or mid or const? And just some, here is a helper function to get a sequence length, provided the sequence ID. And lastly is you often want to test your system in some ways, right? Like maybe just some physical testing. And here is just one example. So I noticed some issues about the Zaber motor, and I want to test it. Well, I want to debug it. So then I write some testing code, and this is the code to do testing. Of course, this this function is in the reader under a certain command. Yeah, under the test command. Whenever I type test, and we'll do the test function. So yeah, so I will skip the demo. Because you guys see me demoing this every day. Yeah, so that's it. That's all I'm planning to talk about today. So maybe that's not that's too detailed, especially the introduction is a little bit too long. But I really want to like keep everybody on the same page, and then in the future, if someone new wants to learn it, so they can learn it from the more preliminary topics and building all the way up.